Most data engineers prepare for interviews by memorizing tools. But in a system design interview, the interviewer is not really asking, do you know these tool names? They are asking, can you design a reliable data platform when the data is messy, late, duplicated, and business users are waiting for dashboards? Hello everyone, welcome to Big Data Fact. I am Ranit and I have 4+ years of experience working as a data engineer. If this is your first time visiting this channel, don't forget to subscribe for more content on big data and real world insights. So in this video, I'm going to solve one full data engineering system design interview question like I would in a real interview. I will show you how I ask clarifying questions, how I choose between batch and streaming, how I design the storage layers, how I handle failures, and how I explain the trade-offs like a senior data engineer. And at the end, I will give you a simple framework you can reuse in almost any data engineering system design interview. So here is the question. Imagine you are designing a data platform for an e-commerce company. The company has orders, payments, product views, refunds, customer data, and marketing campaign data. Business teams want hourly revenue dashboards. Analysts want clean tables for reporting. The fraud team wants near real-time alerts for suspicious transactions. And leadership wants the system to be reliable enough that they are not asking why is the dashboard wrong every Monday morning. So the question is, design the data platform for this company. The biggest beginner mistake is jumping straight into tools. A beginner answer sounds like use Kafka, Spark, Airflow, Snowflake, and dashboard. That is not enough. A better answer starts with clarifying problem. In a real interview, before I draw any architecture diagram, I would ask questions like, what is the data value? Are we processing thousands of events per day, millions per day, or billions per day? What is the freshness requirement? Does the dashboard need to update every second, every hour, or once per day? Which use cases are real-time and which are batch? Do we need to support historical backfills? What happens if data arrives late? Are duplicate events possible? Are there compliance and security requirements? And most importantly, who consumes the data? Because a fraud team, an analyst, and a finance team do not need the same type of pipeline. This already makes your answer stronger because you are not designing a random architecture. You are designing around requirements. So let's define some assumptions. For this system, I will assume orders and payments need to be accurate. Revenue dashboards can update hourly. Fraud alerts need to be near real time. Analysts need clean historical data. Late arriving data is possible. Duplicate events are possible. And backfills are required. Now we can design. At a high level, I would divide the system into 5 parts. Data sources, ingestion, storage, processing, serving, and monitoring. The data sources are things like application databases for orders and payments, web and mobile events for product views, third-party marketing data, refund systems, and customer profile data. For ingestion, I would not use the same approach for everything. This is where trade-offs matter. For product views and fraud-related events, I would use streaming ingestion, something like Kafka or Kinesis. Why? Because fraud detection needs low latency. But for orders, payments, refunds, and marketing data, hourly or scheduled batch ingestion jobs might be enough. This is an important point. I would not stream everything just because streaming sounds cool. Streaming adds complexity. If the business only needs hourly dashboards, batch or micro batch is often simpler and cheaper. So my first decision is streaming for low latency use cases, batch or micro batch for analytics and reporting. This is the kind of trade-off interviewers like to hear. Next, storage. I would use a layered data architecture. We can call it bronze, silver, and gold. The bronze layer stores new data exactly as it arrives. This is important because raw data gives us replayability. If a transformation breaks or if a business rule changes, if we need to backfill 1 year of data, we can go back to the raw layer. The silver layer contains clean and standardized data. For example, clean orders, clean payments, clean customers, clean product views, and clean refunds. This is where we handle schema normalization, typecasting, deduplication, basic validation, and standard naming. The gold layer contains business-ready tables. For example, daily revenue, hourly revenue, revenue by product, revenue by country, customer lifetime value, fraud alerts, and marketing campaign performance. This separation matters because one of the biggest problems in data platforms is mixing raw, clean, and business logic together. When everything is mixed, debugging becomes painful. When the dashboard is wrong, nobody knows where the issue is happened. Was it an ingestion? Was it a transformation? Was it a business logic? Or was it a duplicate event? The layered design helps us debug and scale the platform. Now let's design the batch side. For orders, payments, refunds, and customer data, I would ingest data on a schedule. Depending on the source, this could be CDC, API extraction, database replication, or scheduled file ingestion. The raw data lands in the bronze layer. Then an orchestration tool triggers transformations. For example, ingest raw orders, validate file arrival or source freshness, clean the orders table, join orders with payments, apply business logic for revenue, generate gold tables for dashboards, and then run data quality checks before publishing the data. The important part here is that data quality checks happen before the data reaches to the end users. For example, order ID should not be null, payment amount should not be negative. Each order should have at least one successful payment. Revenue should not suddenly drop by 90% unless there is a known business reason. And freshness should be within the SLA. If these checks fail, the pipeline should not silently publish the bad data. It should alert the team. Because in production, a successful job does not always mean correct data. This is one of the most important lessons in data engineering. Now let's design the streaming side. For product views, cart events, checkout events, and fraud signals, events come from the application into a streaming platform. From there, a stream processor can calculate suspicious activity. For example, too many failed payment attempts, multiple cards used by the same account, order from unusual locations, very high value transactions, and velocity based fraud patterns. The output of the stream goes into fraud alerts table or a alerting system. But I would still store the raw events. Why? Because fraud rules changes. If the fraud team creates a new rule tomorrow, they may want to replay previous events and see what would have been flagged. So even in streaming, I want raw event storage for replayability. This is a strong interview point. Streaming is not just about low latency. You still need durability, replay, monitoring, and correctness. Now let's talk about the data model. For analytics, I would build fact and dimension tables. Some example tables: fact orders, fact payments, fact refunds, fact product views, dimension customers, dimension products, and dimension campaigns. Then goal tables like Mart hourly revenue, Mart daily revenue, Mart product performance, Mart customer lifetime value, and Mart fraud alerts. I would make sure each fact table has a stable business key. For orders, that might be order ID. For payments, payment ID. For events, maybe event ID. These keys matter because they help with deduplication and idempotency. Idempotency means if the pipeline runs twice for the same data, it should not double the revenue. This is one of those words that sound complicated, but the idea is simple. Running the same pipeline twice should produce the same correct result. That is production data engineering. Now let's handle one of the biggest real world problems: late arriving data. Imagine an order happened yesterday, but the payment confirmation arrived today, or a refund happened 3 days later, or a mobile event was delayed because the user was offline. If our pipeline processed only based on the processing time, we may miss these updates. So I would design around event time and processing time. Event time means the business event actually happened. Processing time means when our system received it. For revenue dashboards, I would allow a correction window. For example, every hourly run could reprocess the last 2 or 3 days. For larger backfills, the pipeline should support running for a selected date range. This is why partition by date matters. It lets us reprocess a specific time period without computing everything. So for late data, my answer is use event time, keep raw data, partition historical data, support backfills, and make goal tables update safely. Now let's talk about failure modes. This is where many interview answers becomes weak. A real system can fail in many ways. The source database can be down, a schema can change, events can be duplicated, a file can arrive late, a streaming consumer can fall behind, a transformation can produce bad data, and a dashboard can become stale. So I would design monitoring around three things: pipeline health, data quality, data freshness. Pipeline health tells me whether the jobs are running. Data quality tells me whether the output makes sense. Data freshness tells me whether the data is up to date. I would also add alerts for SLA violations. For example, if a hourly revenue table has not updated in last 90 minutes, alert the data team. If row count drops below an expected threshold, alert. If duplicate order IDs appear, fail the pipeline. If schema changes unexpectedly, quarantine the data and stop publishing. This is the difference between a demo pipeline and a production pipeline. A demo pipeline only works when everything is perfect. A production pipeline knows how to fail safely. Now let's talk about cost. A common mistake is over-engineering. Not everything needs Kafka. Not everything needs real-time processing. Not every transformation needs a huge cluster. For this design, I would use streaming only for fraud and real-time use cases. For dashboards and analyst tables, I would use scheduled batch or micro batch processing. I would partition data by event date. I would avoid reading unnecessary columns. I would use incremental processing where possible. And I would monitor compute cost, storage growth, and job duration. The senior answer is not just the system can scale. The senior answer is this system can scale while staying understandable, recoverable, and cost aware. So if I had to summarize my final interview answer, I would say this. I would design a hybrid data platform. For low latency use cases like fraud alerts, I would use streaming ingestion and stream processing. For revenue dashboards and analyst tables, I would use batch or micro batch pipelines. All data would land first in bronze layer for replayability. Clean and standardized data would go into the silver layer. Business ready marts would go into the gold layer. The system would support deduplication, schema handling, data quality checks, freshness monitoring, alerting, and backfills. I would partition the data by event date, use stable business keys for idempotency, and avoid streaming everything unless the business requirement actually needs it. That is the answer, not just tools, but requirements, trade-offs, reliability, and business value. So here is the framework you can remember for your own data engineering system design interviews. First, clarify the requirements. Second, separate batch and streaming use cases. Third, design raw, clean, and business ready layers. Fourth, define the data model. Fifth, handle late data, duplicates, and backfills. Sixth, add monitoring, data quality checks, and alerts. And seventh, explain cost and trade-offs. If you can do that, your answer will already be better than someone who only lists tools. Because data engineering system design is not just about drawing the most complicated architecture diagram. It is about designing a system that can be trusted. And that is what companies actually need. Comment pipeline if you want more this type of videos. If this helped, drop a like and subscribe to Big Data Factory. This is all for today. I will see you in the next video. Till then, keep learning and keep building. Bye bye.